Hello. February 3rd, 2023. Let's see if we can solve problem 2, or get started with it at least. So we usually let G be a group, but here we'll take it as a ring later on, but it must be the additive group they're talking about. On the other hand, any function is defined that way, then we must prove this. So we start on the right hand side. And then we substitute the definition of the Fourier transform. And it's a finite sum. And it's f of b Now that's not so bright, really. We should rather sum in this one over C. And then it's f tilde of a, so that's minus ac. Plus a b minus c. And if b minus c is distinct from naught, then the sum vanishes. This is modulo n, of course. But we only sum like among the residue classes, so that doesn't really matter. So we only get a contribution when b equals c. And then it's n delta b minus c. So that gives n f of b as it should. Right. That was question A. I expected that to be easy. On the other hand, problem B. First we define this sum, and then, which seems totally unrelated to problem A or the definition above, we start on the right hand side as well and forget the reciprocal of n. right. Now what can we do? I would like to take the summation over A out and do that in its own right. And this converges absolutely. So we can do that. This actually begins to look like the Fourier transform we had up here. So they are actually connected. And the Fourier transform of, or maybe, oh, I don't know. Then we have to take this into account. I had hoped to get G of chi bar, of course, and then we could use the formula of problem 9. Where n is the the norm of the ideal. That didn't come so easily. Another idea is to use the definition of G based on now what's this called? Zeta? Xi. It's Xi. And then reduce that. Let's try that as well. To do anything, we have to change variables here. Can you hear the wind blowing? It's not a storm, but it's a cold wind. So It's actually a little cold where I'm sitting. I don't like this idea particularly. Now G was actually defined like the inverse Fourier transform here. Several times in the previous exercises or problems we've been close to defining the Fourier transform. That's the inverse Fourier transform, my God. But since it's really generated by f of 1, then I thought it would be trivial, so I never worked on it. That comes to punish me now. I mean, if we call this f of chi, this is a number. I'm confused. Lovely. If we take the conjugate, that's the Fourier transform of chi evaluated at unity. I'm going around in circles here. time for a break. I'll make a cup of coffee and see if I get an idea. Here, a few minutes have been lost. I believe I found a mistake, and hopefully the only one. Here, psi, that's the wrong color. This xi to the x, and here we have minus, so it's all the conjugate we get, so it's g of chi conjugated. Yeah. So it's g of chi conjugated. And that's of course the norm of g of chi squared, and that equals n L of chi point s. There we go. That was surprisingly confusing. I will just make a small break where I write the formula again. And from problem 1, we have that this sum converges so long as the real part of S is positive. And since the other sum here is finite, there should be no problem multiplying term verse. So we can just set S equal to unity. No idea. I thought it would lend itself to an idea. On the other hand, maybe this sum can be computed explicitly. Let's try that over here. I feel silly that I don't know what that gives. Oh, we should have an A up here. Let's call that f of A and then differentiate it. This, of course, should be done for some s and then taking the limit, but let's just do it pointwise and see what happens. Then n cancels. Yeah, and then we have a diverging series here, so it doesn't work. A day has gone. It's now February the 4th. I looked at a lot of examples using Mabel, and it seemed to be able to compute this infinite sum. Here we have n equals 2, n equals capital N equals 3, capital N equals 4, and 5, explicitly written. And it seems to know the sum. It can even do it in general, assuming R is real. Finally, it dawned upon me that what was happening here was the series expansion. Its radius of convergence is unity, so it converges absolutely if the modular of z is less than unity. By the way, I just corrected the mistakes I made here. Now, about convergence on the unit circle, I can't solve the problem. We of course have the essential singularity here. And then the circle or the disk or the radius is unity. So it converges absolutely within the disk. And apparently it converges conditionally on this disk, but I can't prove it. I actually looked through this book by Rudin, Real and Complex Analysis, to see if there was an exercise dealing with these problems. I didn't find it really. I found something that looked a little like it, but it was as if they didn't concern themselves about the actually... I don't know if there was a problem. Never mind. Let's assume that it converges on the blue part of the boundary. That means that this summing over n and therefore L of chi point 1 equals d of chi divided by n sum over a then chi bar of a It's a finite formula. I don't know if you could call it simple, but all right. And now let's go to D. Where we have n squared. You can't see it. We have n squared here. Set s equal to 2. Divided by n squared, and they introduce the dilogarithm. Actually, there is a function already called dilogarithm, so that's why it's in this, I don't know what that's called. I have heard it, but or rather seen it. Was it called L2 of chi to the minus eighth? I believe that does it. At least that's as far as I can get.